Anyway, and this section we try to discuss about how to control the brushless DC motor. Before I prepared this lecture, because I was thinking, so I teach you the control this brushless DC motor because we still have quite a number of other material to cover, right? So today is a week 13. So we have 14, 15, and 16, but next week we only have one lecture. So I'm not quite sure it will cover everything. So, but that will be something nice to show you how we control that. It's a very short chapter, show you how we're going to control the brushless DC motor. So, and the thing is, you don't have too much background on power electronic. So in here, we do need to use a lot of power electronic, how to control that. So, but just, if you don't understand, don't bother too much about it. In here, just show you our concept, how we're able to control, especially using the kernel control the DC motor. So you try to, a part of your library, so after you learn the power electronic, you can understand much more about what it is. So in this chapter, we're going to show you how the basic configuration, the construction for the brushless DC motor, how we examine about the control method. So most of the motor, we control them mainly to control the torque. Torque control will be most important because once we control torque, we are able to control the speed too. So to control the torque mainly is to control the current. So we're going to show you the current mode control here. Current mode control in power electronics are quite simple. So we can able to use the transistor to control how the current pass through certain inductor. The inductor will be, in here will be the motor inductor. So that's how we try to do that. We also show you about how to calculate torque and how to work with the torque ripple too. So in here will be, do you think the control of brushless DC motor will be the same as the DC motor? Both of them we need to control the motor torque or cause the motor current. I haven't shown you how to control the DC motor current properly, but the control concept will be the same here. Once you understand how to control the brushless DC motor, the current mode control, then you can do something similar to the DC motor anyway. But both of them will be quite similar because we both tend to control the motor current. So, but of course, in here, we do need to have position sensor. For brushless DC motor, the sensor will be important. We really need to know the exact position for the motor in order to control that. And what do you think the market share for brushless DC motor compared to the DC motor? Have you been using many of the brushless DC motor? Or your appliance, which appliance you are using now are brushless DC motor? All the computers are using brushless DC motor. No computers are still using the brushless DC motor. You can now have a really small brushless DC motor. They're good for the cooling and along the application. But however, for some large household machine, even though some power drill or maybe the washing machine, some old washing machine, is still using the brushless DC motor too. Because probably it's quite a mature product, they still continue to use it. So, do you think the efficiency of the motor will be affected by this new motor drive? Brushless DC motor, we have to use a motor drive, power electronic motor drive. Do you think if we use brushless motor, will the efficiency be affected?
Slightly.
Slightly. Should be slightly. Look, sounds like slightly. Huh? So let's go through the chapter, then you know more about how the combination. So, and one thing will be using brushless DC motor will be we can able to power electronic to control voltage with the motor. So we can use all the duty ratio, for instance, to control voltage applied to the motor. So do you think if we change the voltage, say a DC source, we go 48 volt, 100 volt, and then we charge power electronic to reduce the voltage, do you think that will affect the efficiency to the motor or to the whole system?
I think it depends on the power electronics circuit. Like if we, like let's say we use diodes, it would have less efficiency compared to if we use just transistors.
Yeah, that's a pretty good guess. If we add on anything, there must be something affecting the efficiency like power draw, transistor, diode. So let's see how this will look to show you the answer. So actually, the effect of the efficiency due to power short is really minimum. So this chapter, we're going to go through the how we control and also the driver look like, and then we also go through a number of tutorial. So this small chapter will just show you how the operation like. So the key thing we like to show here will be mainly about we try to use a DC or battery source in order to drive the brushless DC motor. We also need to detect the motor speed. We also need to develop how to close loop the speed. To close loop the speed, then what we need to do will be we need to detect the position for the motor. We also need to detect the current to do that. So all the closed loop control, we need to basically close the loop for the torque loop. We are able to control the motor torque. And then next, we can therefore develop the closed loop control for the speed. So we still based on the same torque equation. The torque equation shows us if you want to control the motor torque, we need to control the motor current. To control motor current, of course, we can measure motor current. So for all this kind of brushless motor, if you want to control the motor operation, we need to measure the motor current. So the motor current may not be pure sinusoidal, as you in the left, the waveform is quite special. But for ideal waveform, the waveform more look like a square wave. But when the transistor being turned on, the current will be more look like a DC current, simultaneous DC current. So basic method to control the torque will be have to develop the current control to control the current. So that's what this chapter trying to use a method how to show you a typical method how we control the motor current. So you can see that the transistor arrangement will be in such a way. Every time that we have to connect with two winding, it's a Y connection. So when we turn on the two transistors, like in here, we are expecting we're going to see the current are being flowing in such a way, right? We turn. So that means we, by this manner, we can apply a positive voltage to the transistor. So this positive voltage, similar to conventional DC motor, we just excite the two winding together. So in this case, when we model them, try to understand how much current we go through them, we can just consider them as a resistor and also a back EMF. Then, of course, we do have winding here, appear as an inductor. We can also model them, but depend on which condition we want to model them. If we want to model them in the steady state, we don't worry too much about it. But however, in transient state, when we use high field switching, we do need to include the inductor for the modeling. So that's how the current look like. We're expecting we have higher input voltage and then pass through them so the current become positive in here. But so this is one of the region of operation. But for more detail, then you can see that if you want to regulate this current pass through the I current, how are we going to do that? Can you recommend to me how we can regulate the current pass through the two winding? Can we control the current pass through that? You see, if we turn on the two transistors indefinitely, of course, you can see the current will increase indefinitely. Of course, we don't allow that. So how are we going to control this current to stay a constant current unchanged? What we can do to do that? Yeah, Peter and method. That means we try to make it become a square wave to turn on, turn off in high frequency to hold the current in certain position. So to do this one, you can see that in this manner, this I current, when we turn on, will be increasing. We don't allow it to increase to too high. Go to when it reach certain position, you can stop the current. Don't allow it to increase, and then somehow we will decrease it. And when we reach something, we increase it and decrease it, and then we can control the average current to be certain amount. So that's how we're going to do that. So we use some switching manner. Then in this case, we become N on, off, to do that. So when we turn on, then we off. Okay, next cycle we turn on. So on will be in here. Right? We try to turn on. Turn off. How do we turn off this coordinate transistor? Quite straightforward. You turn on any one of the transistor. What happens to the current? Any one of the transistor. Then let's see what happens next if we turn off one of the transistor. So if this is off, then the current already looping in here will try to complete the loop in such a way. Then in this case, do you think the current under that condition will be increasing or decreasing? You turn off the bottom transistor. You don't turn off both of them. You only turn off this one. And still maintain this on, right? Then we can see that the current must be looping in such a way. Then you will ask me, the current is flowing in here. And then when current goes to this point, you cannot go down here because transistor already turned off. But the inductive current cannot stop instantly. The current has to continue to flow. So that's why current will go to the top diode, complete the loop. So that's how it happens. So now the current will be looping in such a way. You will compare to previous one. The current VDC driving in here, turn on, and current will turn to here, right? That's how the current loop. So in this case, you can see that DC voltage applied to the whole of the winding, create full back EMF and full voltage drop on the whole resistor. And then next, if you turn off the bottom transistor, then this current will therefore looping in this manner. The first one, we know the current will be increasing because usually we make sure that the VDC voltage is higher than twice of the back EMF. We usually, so that the IA become positive. We have positive current, positive torque, right? And then next will be, if like that, then we have no input current. So we have no input voltage. And then the current will therefore looping in such a way. So what happens with the current? In this case, with the current increasing or decreasing? Decreasing. Why is that? Because the back EMF is the opposite direction to the current. Even we have no input here, the back EMF will force the current to decrease. Not the opposite, the current need to change slowly. The current can instantly reverse. So the current will therefore drop it. So under that condition, for any instant the current is in this point, you just decrease. So in the off state. So in the on state, the current has been increased, but now then the current is now dropping. So when the current drops to a certain point, we turn on again. So that's why in that zigzag manner, we can maintain the current to position a certain average current. So that's how we're trying to do on, off, and then continue to do that. So we can therefore maintain the current rest in certain average current. That's how we're going to control. That's the basic concept. How we use θm method to control the current. So we never will turn on indefinitely. So this period here, quite small. This period also quite small, talking about microsecond, really fast speed, and then we try to control the current. So the basic how we're able to adjust the current operation. Up to this point, any questions? Good. So before we also a switching pattern in such a way. So again, if we turn on the transistor in this kind of the manner, Again, every time we have two of the winding are being turned on. And each column or each position, we have 60 degrees of operation. So that's more ideal line waveform. So we assume the current here would more look like a square wave in this kind of the pattern. So under this manner, then if we work out the equation, it will be like that. So when we rising, then we got input voltage here minus all the back EMF and also the voltage drop, and divided by the inductor. We have two inductors here, right? Then that's how the dIdt look like. Very simple inductor equation. I think you all learned that equation, right? LdIdt equation. And then when you turn off in here, so turn on will be in here, right? On. And then when we turn off, then this current will be looping, close the loop in here. Then the VDC without the current equal to 0, no DC voltage. So you can see that these terms are all negative. Negative doesn't mean the current reverse, but just dropping the current. So that's why you can see that this current is now dropping. So that's how the formulation look like. So that is to say, when the lower device is on, we complete the driving loop in here. But of course, we use V dash here, mean the voltage drop after the two transistor. And then when U is off here, this one equal to 0 in here. So that means you can see the equation here. This one is positive, this one is negative. So that is so how the dIdt being changed. So that also gives you the ripple. Later on, we also calculate the ripple. What time is it now? Still have time. Yeah. We are leaving. This time is trying to show them all. There's a low coffee at time. But anyway, so you can see here, the model will be the same as what we have been doing. The E dash equal to 2 of the back EMF, R dash equal to 2 times of the base, and so on. The inductor, full inductor here. The voltage drop with DC input minus 2 transistor voltage drop. So that we have our equation. So next, in this equation, do you think we can work out the average curve? So what we like here will be, we only know the ripple going up and going down. But what we want, because this ripple supposedly to be really small, tiny, because we're using really high frequency to do that, the ripple probably, I draw it in that exaggerated manner, but actually the current will be like this, probably very small, very tiny. We won't have such a high ripple. This ripple only to show you the variation, but actually for motor control, when we use really high frequencies, then this will be really only just 1%, 0.something%, with just a few percent. You won't see that thing. So that means what we can see here, more of DC current, more look like the average current. So that's to say, if you want to calculate the motor torque, we can still using the average current to calculate motor torque current. The next will be how we're going to use this method to determine the average current. Do you think you can do that by controlling the on and off manner to control the average? What do you think? We can able to control turn on, turn off. How do we control the average current? This current. That's what we're trying to do, right? Control this current so that we're able to control the average torque for the motor. We're not going to control up and down torque, we only control this torque. So you see, we have a fluctuation for the current. We may have some fluctuation for the torque, but again, this is really small, so the torque doesn't change that much, only quite stable. Together, the torque motor have a large motor, which are good inertia, can actually look like filter to filter all the people. So what you come out from the shop will be really stable or anything. So that's how why we can use high frequency to control it. Because once you use high frequency, the ripple will be really, really high frequency. For instance, if you 100 kilohertz, probably the shop, the motor cannot vibrate 100 kilohertz, impossible. So that's how we use more like a filter, a motor becomes a filter to filter the high frequency. So that's how we're going to do that. So now then the question will be, can we control the FH curve by using this method? What do you think? Can we control it? Must be, because that's my lecture. Huh? we must able to control it. So let's to see how do we work on the average in here. So in this equation, V dash is given, is known, input voltage, right? R dash is the motor parameter. We know we can measure it. Inductor, we can measure it. Then E, of course, we also know all this. So, and then dI, we may need to calculate what kind of dI in here. And dt, this one, we know what's dt.
Like for the cycle comes the frequency works.
Yeah, how we turn on the transistor. So if that is the period, right? You always say period. Say the period is switching period. So that's the turn on time. We got the duty ratio here. So probably this is equal to dTs, right? The rest of them will be 1 minus dTs. So this will be dTs. This will be 1 minus dTs. So now we know everything. We should be able to solve the equation to get the I average. So that we say from these two equations, we can able to relate the I average to the duty ratio in 3. So that is to say we are able to change the duty ratio for our transistor to control the I average. So the key thing we like to do. So that's to say, originally the circuit is like that for each column of operation. For each column, although we try to say the column will be say on these two transistors, but actually more detailed will be try to have high frequency on and off this transistor to control the current. So this one of the operation, of course, you can say, oh, can we turn on this one all the time, switching this one? Yes, of course. If you do that, you can also do the similar manner. So there's another flexibility to control. But once you fix your circuitry, you can determine which transistor we want to have high frequency switching to control the current. All right. So now then, so to do this one, we're putting these two equations together. Why is that? How we can put them two equations together? The left-hand side is the one going up, the I. The right-hand side here is going down. So why are we putting them together? Why? What kind of theory behind?
Some of them should be 0.
Why 0?
It's a closed circuit.
Closed circuit. Close enough. I like a better answer.
Yes. ODE.
Huh?
ODE.
So say again?
Ordinary differential equation.
No, not that. This part, the left-hand side is going up ripple, the right-hand side is going down ripple. You see when you control motor, when motor becomes stable, then that is to say when going up, going down must be the same. If not the same, the motor probably go up indefinitely, become really huge current, or you going down indefinitely, become very small current. So when motor becomes stable, they're going up EI and going down EI must be equal and opposite to each other, so that the motor becomes stable. We're talking about stable control of a motor. So in this case, you can put these two add together, become 0. So that's how the manner we can work on. So once put them together, You can solve the equation, you can get I average now equal to this beautiful equation, simple and beautiful and useful. Only single ratio is control temperature. So that's to say you control the ratio of that particular transistor, you can therefore control the curve. Simple enough. So that's how far we can use power electronics to control current sources. You see in the first few chapter when we the DC motor, we use the chopper, so inconvenient, so expensive to do that. But now we use this bridge inverter, so we can able to control the field ratio and control current for the motor. So that's how we try to do. Any question up to this point? Good. Nine. I think now you like the motor. How we control this motor in this simple and beautiful manner. Okay, see you on Wednesday then.
Are we gonna have class Thanksgiving week?
And yes, for next week, Monday we still have class. Wednesday, do you like to have a class?
Yes.
Next week, are you sure?
Yeah.
100%. I speak
for the class.
This Wednesday, for everybody will disappear on Wednesday.
I'll not be here. Even have class, there's not an instruction class.
Monday this week, but we not going to have lecture on Wednesday, right? So everybody disappear. I don't want 100%. So get you
0% of survey people.
100% of survey people said we should. What did you have?
No.
100% said
No.
no. This Friday.